Okay, in this video, we're going to be talking about filter circuits. In particular, we want to be able to understand plots of Z versus omega and I max. And I'm going to have to hit the pause button in just a second here. Okay. All right. And so we've seen how to, if you have numbers, you can plug in and make spreadsheets and make these plots. But I feel like it's important to also understand these conceptually. This is how we started this unit. Remember, I talked about this conceptually. So this is actually a bit of a review. But let's see if you remember it and go through it one last time just in case. So here we have a circuit, and we have what I'd like to do is be able to just guess what these plots should look like and sketch them. Now, if you recall, I'm going to go over here to this circuit. Let's go to here. I've got my old friend, and now in this case, we have a very, we see that this light, we can see that the brightness or the current amplitude varies depending on what frequency you use, right? Now, in this case, if I go to extremely low frequencies or extremely high frequencies, we don't see any light at all. So we already can tell the current amplitude should basically be 0 at high and low frequencies for this LCR circuit. And remember, these are just here to give us an indication of the current flow. But now, in order to make this a little bit more visible, what I'm going to do is I'm going to put some capacitance in parallel. Now think, if I add capacitance in parallel, what does that do to the total capacitance? This is a huge capacitance, by the way. This is 0.1 farads right here. So, whoops, let me bring it in. There it is. So there's this large capacitance. Okay, so basically, when I put this capacitor in parallel, I add to the total capacitance. And since this one's so small, now this is effectively the capacitance. It's just easier for me to connect everything like this. Well, in this case, what's the formula that we know? So I'm just going to do a little scratch work here. I know that omega naught is equal to 1 over the square root of LC. So if my capacitance goes up really high, my resonance frequency goes really low. So now hopefully what happens, if I go back to my demo, if I add a lot of capacitance, hopefully now what happens is I could see this thing at low frequencies again, so we can talk about it. And all right, in this case, I actually had a number approximately written down. I think the resonance frequency is close to 1 or 2 here. So in this case, we could go all the way down. And actually, this is actually close to resonance. And now as I raise this up, if I go up to higher frequencies, we see as you get to higher and higher frequencies, it drops off. So that's just to help us see. So again, now what are we trying to do? Let's go back to our main picture. We're trying to understand the brightness of this bulb as a function of omega. All right. Well, in this case, the trick is to remember the following things. All right. And if it helps, well, I'll reference. All right. We know that X sub C is 1 over omega C. At low omega, X sub C goes to infinity. At high omega, X sub C goes to 0. Got it. I know that X sub L is equal to omega L. So the opposite is true. At low omega, X sub L goes to 0. At high omega, X sub L goes to infinity. Well, this begs the question, what does it mean to have infinite resistance? Well, let's go over here to this circuit. If the inductor had infinite resistance, that would be the same as being an open switch. So in fact, and having 0 ohms would be like a short circuit. So let's see what this might look like in just a second here. For now, I'm going to leave that there. There's one other special frequency that I want to discuss. At omega naught, we know x sub L is equal to x sub C. Well, let's think about the consequences of this result. Z will actually equal the square root of R squared plus x sub L squared, x sub L minus XC, quantity squared. Well, if x sub L equals x sub C at resonance, Z is equal to R. Aha! We see a couple of interesting things here. At low frequencies, the capacitor will dominate, and there will be basically infinite resistance and no current flow. At high frequencies, the inductor dominates, has infinite resistance and no current flow. At resonance, the resistance doesn't go to 0, but it actually goes to this resistance level R. If I tried to sketch this out, what would that look like? Well, the Z is infinite here, and it's infinite there, and then at some point it comes to a minimum, right? That minimum value has value R at special frequency omega naught. This is a quick way to understand what the plot of a series LCR circuit would look like. Great. We already knew this because we did the plots. But what about the current amplitude? Well, let's look. At omega naught, well, I know that the voltage of the source divided by Z gives me the peak. Well, at resonance, Z equals R. So this happens to be the one special frequency where you could take the source voltage and divide it by R. That is the peak. And then over here, where Z is equal to infinity, there's no current. Over here, where Z is equal to infinity, there's no current. So we see we get something that looks maybe like this. All right. This is a plausible sketch of current amplitude. Right? This is not current as a function of time, it's current amplitude as a function of omega, which relates to, if you recall, the average power was equal to I RMS squared times R. Well, think, I RMS is I max divided by √2. So, right, the idea is this is a little bit like the plot of the power. Right? If we know the current amplitude as a function of omega, in theory, we could figure out the average power and the brightness of the bulb as a function of omega. So far, so good. Now, if you want, you may want to look at question 31.13. All right. And I'm going to draw that up real quick here. Let's go to board 6. All right. So the idea here is we have different components. We have an inductor, we have a capacitor, we have an inductor and a capacitor in series. And then I'm going to discuss one other option, and I'm just going to kind of give you some insight here. We have an inductor and a capacitor in parallel, all right? Now, we also have different frequencies. And I'll try and match this plot to whatever there. All right, so basically we've got several different frequencies we can discuss in all these different objects. And I want you to start thinking like this, okay? At low frequencies, the inductor acts like a short. You can replace the inductor in any of your circuits with just a straight wire or a closed switch. The capacitor, however, looks like a break. So sometimes you'll hear me say, the inductor looks like a short, or the capacitor looks like a break at low frequencies. Now, in this case, over here, at high frequencies, they switch. This is a break or an open switch. Oh, there's my phone. Hold on. Hey, I'm in the middle of a bid. I'll call you back, okay? I'll get back. Yeah, I'm getting close to done. I'll call you back. Sorry about that. It's been a long day and I don't know. I'm not re-recording this video, so too bad. This is a brutal day. Sorry about that interruption, though. All right. Okay. In this case, when you have low frequencies, the inductor is a short, the capacitor is a break. When you have high frequencies, the inductor is a break and the capacitor is a short. You can tell I'm tired. All right. Here's what's special about when you put them in series, right? When you put them in series, all of a sudden there's a resonance frequency. For these two, there is no resonance frequency. Not applicable, not applicable. But this one, at resonance, it looks like a short. Okay, why? Because at resonance frequency, these two balance out. Now at low frequencies, the capacitor is going to make it act like a break. So the net effect is a break. At high frequencies, the inductor makes it look like a break. Well, if you had to guess, think about what putting an inductor and capacitor in parallel would do. Well, in this case, at low omega, we know something about this. We know the inductor acts like a short, the capacitor acts like a break. Well, the net effect is a short. So when you put a capacitor and an inductor in parallel, we see the inductor makes the whole thing act like a short. Similarly, at high frequencies, it's exactly the opposite. It still acts like a short, right? The capacitor this time is acting as the short at high frequencies. The capacitor doesn't have enough time to charge up. Well, I wonder what happens at resonance. In this case, well, I'm just going to say it's equivalent to a break. And I'm not really going to go into the math unless that, if you want to understand the math of this and where it comes from, you could look at some complex number theory, which is on page workbook problem 31.18 and 31.19. I explain why it looks like this, but that's beyond the scope of this course, and I don't want to go into that. All right. And so the idea here is you can use this information to sketch out these plots. If you know this information conceptually, that helps you sketch out what Z or the current amplitude will look like as a function of voltage. And so as practice problems, I give you a bunch of these, but maybe let's do, I'm going to make up one that's not, oh, actually, how about this? Let's look at, I'll just make one up. I'll make one up really quick. All right. All right. Well, let's say we have a circuit that looks like this. All right. Actually, let's use the inductance. It'll be easier for me to rewire over here. All right. So we've got a source voltage here. And I don't know if you know this, but these function generators always have a small amount of resistance here. So there's always some load resistance in here, internal resistance. So this is going to be our resistor load, or our load resistor. And this is going to be the internal resistance. So again, this is just a made-up problem. Here's the inductance. So what we want to do is we want to figure out how this thing's going to operate at a low frequency. So I just redraw it. At low frequency, I still have my internal resistance R, I have my load resistor R, but the inductor acts like a short. Well, in this case, Z equals R, the internal resistance, which is approximately equal to 0. It's not exactly 0, but it's very small. That means we should not get much current through the resistor, right? So that means the current through our load is small. It's effectively 0. Now there's still current through the entire circuit, but just none through the load resistor, right? It's short circuited, right? If we go to omega high, we still have this resistance. We still have this resistor, but at high frequency, the inductor acts like a brake. Well, in this case, Z is equal to R plus R, which is approximately equal to the load resistance. And we see the current amplitude through the load resistor is the source voltage amplitude divided by resistance. Aha! Well, if I wanted to plot these things, I could make two quick plots. I could plot Z versus omega. And I could use this to see, oh, at low frequencies, Z is 0. At high frequencies, Z is equal to R. So it's going to taper off. Maybe I'll make this plot look a little bit better. The maximum value of the impedance is R. Well, what is the current amplitude through the load resistor? So I load resistor max versus omega. Well, we see initially we get a lot of current. It's V naught divided by R, and then it drops off to 0. So it probably does something like this, right? And the idea is we are able to conceptually understand what is happening to the load resistor without having to do all the math. Well, look at what we have created. We are filtering out certain frequencies. In particular, we see this unusual circuit says, well, any high frequencies, and wait, did I flip that? I did. I flipped the current, didn't I? Did I flip the current in the Z? No, oh, I see. Okay, so in this case, I see what I did. I made a mistake. Let me catch up here. All right. So this upper plot is correct. This is Z for total circuit. Okay. And so, but what the second plot was supposed to be current through the resistor amplitude. And I didn't read the wrong words, or I read the wrong words. So in this case, the idea is, I should be reading these second lines. I apologize. The total impedance of the circuit is 0, but the current through the load resistor, right, is negligible because all the current takes this path. So the current is small here, and then it ramps up to some value like this, which is V naught over R. So what we have done is we've actually, if I had read this carefully the first time, and I apologize for making that mistake, in this instance, what we see is there's low frequencies do not pass to the load resistor. The load frequencies, this inductor acts as a short circuit and it filters out all the low frequencies. So only the high frequencies will actually do anything to this resistor. So you could call this a high pass filter where high frequencies are passed to the load resistor, right? You could think of the series LRC as a band pass filter. Only a certain narrow range of frequencies are passed to that. So in this case, I guess what I'll say is, why don't you take a look at 31.6 and see if you can do this kind of stuff yourself, or 31.15 is another example. And that's pretty much a wrap for this chapter. If you want to look and see what this looks like, maybe we should do that really quick since I happen to have it here. The idea was, let me do this. We're going to take this capacitance out and we're going to put this inductance in parallel, right? Now, in order to make this show up, what I'm going to do, oops, hold on. There. All right. So I'm only going to use one diode, so it'll, sorry if it's not blinking all the time. What I'm going to do is I'm going to put this inductor in parallel with this entire resistance. Like that. Okay, so now what we have here, I don't know if you can see that, is this inductor is in parallel with this light bulb resistance, all right? So now what I'm going to do is I'm going to put my function generator in here. All right, and let's see what should happen here. Oh my gosh. All right, so it is kind of working. It's not the greatest here. Maybe my values of inductance aren't the optimum. But so what I'm going to try and show you here is, as I increase the frequency, we should get a larger amount of, oh, and maybe I need to use a larger resistor there, but that might be all it is. All right, in any event, in this case, so as I go to higher frequencies, we should see more brightness of this bulb, right? So let's ramp this up a little bit. So that's the standard brightness at 0. As I go to higher frequencies, there we could see it's starting to be brighter and brighter, right? So as I go to higher and higher frequencies, the net effect is we actually get a little bit of kick in the brightness. And that's what I was trying to show you with this plot right here. So this isn't a perfect example, and I apologize, but we did see, so it looks like in practice, there's maybe some residual resistance in there and some other factors. So this didn't actually drop all the way to 0, but we did see it did climb in brightness once you passed a certain frequency. So that was one of the things that we saw there, and I hope that made some sense. All right, so that's filter circuits. You could do some practice.